Good morning. Well, this is it, the last topic we're going to do before the summer holidays. We get through this, we have come a hell of a long way in the time we've been off. Obviously, we're going to consolidate all this in September, and until I start talking to you, quizzing you face to face, I won't really know how much of this has all sunk in. But I'm sure some of it has, and I'm feeling fairly confident based on your assessments that you've done so far that the majority of this has gone in and that you're in pretty good shape. So anyway, without further ado, de Moivre's theorem. This is a theorem to do with complex numbers. So let me just take you through the start of this topic today. We're not going to finish it today, and see what you make of this. So what is de Moivre's theorem? Well, it's a very simple theorem that can be used for lots of different things, some of which are not actually anything to do with complex numbers, but more of that later. So basically, this is the theorem. It says that if you have a complex number written in modulus argument form, if you can remember what that is written in the form cos theta plus I sine theta. Remember, any complex number can be written in that form. Then if you raise it to the power of n, in other words, square it, cube it, whatever, then it turns out that cos is equal to cos n theta plus I sine n theta. And this is true for any value of n that belongs to the rational numbers Q. Have you seen this notation before? Q is the rational number set. It's not quite as big as the real numbers. It's all the real numbers without that can be written as fractions. So basically, n does not have to be a whole number. Okay, it doesn't even have to be positive, and this result does in fact hold, which is quite a remarkable result, really. So in the exam, you have to be able to prove this, but only for the case where n is an integer bigger than 1. So proof for n greater than or equal to 1, where n is an integer. And I'm going to go through that proof now, but the result, like I say, does actually hold for other values as well. It's a bit like binomial theorem. When you first do it in unit 1 of normal maths, you do it with n being an integer, but then you discover miraculously that it also holds for n not being an integer, for being a fraction or being negative in unit 3. And we're just going to prove the case for this formula for when n is actually an integer. And I don't know what's happening in my camera. It keeps going in and out of focus, and I don't seem to be able to stop it doing it. So I apologise for that, but I'm just going to persevere and ignore it for now and have a play later and see if I can get it to sort itself out. Don't know why it's doing it. Might be a lighting in here or something. So how do we do this then? Well, we do it with induction. We're going to prove this with induction. So first of all, I've got to show that it's true for the case where n equals 1. So when n equals 1, the left hand side would be cos theta plus I sine theta to the power of 1, which is of course cos theta plus I sine theta. You can already see how trivial this is. The right hand side, that's this, would be cos of 1 theta. That's supposed to be a 1 plus I sine of 1 theta. So make it look like a 1. You put the 1 there, but I just wanted to make it clear that I'm kind of subbing into that formula, which is of course cos theta plus I sine theta. Therefore, left hand side equals right hand side, and the result, rather unsurprisingly, is true for the case n equals 1. Now, if you remember proof by induction, you then assume that the result is true for n equals k. Okay, so you assume it's true for the case n equals k, and okay, so we've assumed it's true for n equals k, which means that cos, I'll just write the result out again. I've just changed the setting on the camera which I'm open. We'll sort out our focusing issues. I've changed it from continuously auto-focusing to just doing it once at my command. God, I hope it's worked. Seems a bit more stable now. Assume true for n equals k. Cos theta plus I sine theta to the power of k equals cos k theta plus I sine k theta. Now we have to show that it's true for n equals k plus 1. So we start off by writing the result, well, the left hand side of the result for n equals k plus 1, which is that. And somehow I've got to incorporate that result in there. So the first step is to break this up into two separate things multiplied together. That to the k multiplied by cos theta plus I sine theta. Now hopefully you'll agree that that there is the same as that. Nothing funny going on yet. The next step is then to use our assumption result here to replace that there. So that there, because I've assumed that that is equal to that, I can replace that with that. I hope that made sense. So I get cos k theta plus I sine k theta brackets cos theta plus I sine theta, like that. Now I'm going to mark my equal sign over here now because I need some space. I'm going to multiply this out. Okay, so if I multiply this out, I get cos k theta cos theta, and then I get I sine k theta. So I'm multiplying each of the things in the first bracket by cos theta, and now similar trick for the second bracket. I get plus I sine cos k theta times I sine theta. I'm going to write that the other way around. So I sine theta times cos k theta, and then finally this one here is going to be, well, it's going to be minus, because I squared is minus 1, and it's going to be sine k theta sine theta. There we go. Okay. Right. Okay, so we get that. Now, what on earth can we do with that? Well, the first thing we're going to do is we're going to change the order of it. So we're going to write these two things here as the first two terms. So we've got cos k theta cos theta, and then minus sine k theta sine theta. I'm just going to put those in a big square bracket. I don't know why. Just fancy putting them in a big square bracket. And then plus, I'm going to take the I out as a common factor, and then write in a big square bracket here sine k theta cos theta. I'm going to change the order of this. I'm going to put the k theta first, plus cos k theta sine theta, like that. Remember, our aim is to make this look like this, but with the k's replaced with k plus 1s, because then we'll have gone from the left hand side of the n equals k plus 1 case to the right hand side of the n equals k plus 1 case. So how do you do that? Well, what you have to do is get up out your chair, have a rummage up here somewhere. Be back in a minute. I am still here. I'm looking for something. I found it. I'm looking for this. the formula booklet. Now, this formula, we've already used it earlier on when I think we were doing polar. I alluded to these formulas. It's these fellas here. Sine of a plus b, cos of a plus b. I don't think you've done them in normal maths yet. When you do them, you will find them very, very useful for lots of things. And we're going to use it now. So if you look at this one here, we've got cos. We've basically got the right hand side of this one. Cos a, cos b. Cos k theta, cos theta. So that's my a and that's my b. And then I've got sine A, sine B with a minus sign. So it's the top version of this. So it's cos of A plus B. So in other words, the whole of that can be replaced with cos of, open bracket, K theta plus theta. Like that. Clever stuff. Now, similar trick with the other one, but this time it's using the sine formula. If you look here, I've got sine A cos B, like that, and then I've got cos A sine B, just like that, with the A being the K theta and the B being the theta. And so it's the same sign this time, plus plus, so I can replace it with sine of K theta plus theta. Move that out of the way. Slight new way of writing this would be to take theta out as a common factor. So I end up with cos of k plus 1 theta. I'll put the theta on the end rather than at the start because it'll make more sense. And then sine of k plus 1 theta. And we are done. We have started with cos theta plus I sine theta to the power of k plus 1. And we've ended up with cos of k plus 1 theta plus I sine of k plus 1 theta. So we can now say, therefore, it is true for n equals to k plus 1. Okay. Therefore, by induction, true for all k greater than or equal to 1, where k is an integer. And like I say, hasn't happened yet, but you might be asked to reproduce that proof in the exam. I'm going to be giving you a textbook which has got a copy of this in it, so you can see it for yourself at your leisure. And if you want to see the proof for yourself, it looks just the same as mine really. It's on page 49 of that textbook, if you can remember that. Okay, it's an example in a section on proof by induction actually, so you can see it there. But anyway, that's proving it. What about using it then? What's it for? Well, have a look at this. Again, this is from the textbook, so I'm not making these examples up. I am actually getting them from a textbook, which I will show you what it is in the lesson information. So, start a new page. So, let's suppose we had something like right, so this is the first example in the textbook. Actually, I'm gonna change it. I'm gonna change it. I'm gonna start by starting with a complex number that is not in modulus argument form. Okay, so we're gonna start with z equals. I've got to translate it now. This is going to be fun. So it's going to be root 3 over 2 plus I over 2, or half I. There we go. So I've got a complex number, root 3 over 2 plus a half I. And let's suppose I want to cube it. So I want to find z cubed. So z cubed is going to be root 3 over 2 plus a half I multiplied by root 3 over 2 plus a half I multiplied by root 3 over 2 plus a half I. Okay, and I could do this by multiplying out the first two brackets and then multiplying it by the last bracket. Or I could do it using the binomial expansion method. Okay, Oh, do you know what? Let's do the binomial. See, I'm sure you'd be able to do that. But if we were to do it using the binomial expansion method, it would go something like this. Root 3 over 2 plus a half I cubed. Okay, so it's going to be, so the coefficients are going to, I don't know if you remember all this stuff, are going to be 1, 3, 3 and 1 from the Pascal's triangle. And it's going to be that to the power 3, that to the power 0, that to the power 2, that to the power 1, that to the power 1, that to the power 2, that to the power 0, that to the power 3. In other words, 1 times root 3 over 2 cubed plus, I'm going to run out of space here, aren't I? 3 times root 3 over 2 squared times a half I. I'm going to go on to the next line. Plus 3 times root 3 over 2 times a half I squared. Do you know, I think I've almost done it that way now, which is horrible. And then finally, it's going to be plus a half I cubed. There we go. That is the binomial expansion of that horrible thing there. Okay. So if I now multiply it all out, so root 3 cubed is going to be root 3 times root 3 times root 3, which is 3 root 3. Root 3 times root 3 is 3, so it's 3 root 3. I'm sure you'd probably just do this all on your calculator, wouldn't you? But that's rubbish. All over 8, like that. And then the next one's going to be, oh god, root 3 squared is 3, so that's 9. 9 over 4, so it's going to be, sorry, 3 over 4, so it's going to be 9 over 4 overall, isn't it? So it's 9 over 8, so it's plus 9 over 8i, like that. And then the next one, right, well, a half I squared, this is better work, I tell you, I haven't done all this work. A half I squared is going to be, oh god, minus, it's going to be minus, it's going to be a quarter, so that's an eighth. So, oh, it's going to be it's going to be minus 3 root 3 over 8. Aha, they cancel out, look. And then on the end, finally, we've got plus, oh sorry, it's going to be minus, I cubed is going to be minus I, because I squared is minus 1, so it's minus I, so it's going to be minus, and it's going to be I over 1/8 of I. Okay? And if we simplify all of that, we end up with those cancelling out. 9 over 8, take away an eighth is 8 over 8, so we end up with I. So after all that, z cubed for that is just I. Well, that's exciting. Why did I show you that? Because now the fun starts. What if I was to write that in modulus argument form to start with? In other words, I find the modulus of z, which if you recall you do by squaring that, and adding them together. So root 3 over 2 squared is 3 over 4. So it's going to be that squared, which is the square root of that squared, plus the other one squared, and it ends up being 1. So modulus of z is 1, and then the arg of z is tan to the minus 1. We're in the first quadrant here, so it's root 3 over 2 divided by a half, which is, I've done that wrong, haven't I? First mistake of the video, sorry. It's y over x, so it's the other way up. So it's a half divided by root 3 over 2, which is 1 over root 3, which is root 3 over 3, like that, something like that anyway. And tan to minus 1 of root 3 over 3 is in fact pi over 6. It's 30 degrees. There, so I've got my modulus in my argument, so I can now write z in the form r cos theta plus I sine theta. R is 1, so I won't bother with that. So I just end up with cos of pi over 6 plus I sine of pi over 6. Right, okay, so all I've done is write z, which is given in a plus ib form here, in modulus argument form here, and now I'm going to cube it. So z cubed is going to be cos of pi over 6 plus I sine of pi over 6 all cubed. And this is where our friend Demarvra comes into play, because all we do is apply, where's he gone? Where's he gone? We apply this result now. The 3 means all I have to do is to times the angles by 3. So I end up with cos of 3 pi over 6, otherwise known as a half, plus I sine of 3 pi over 6, otherwise known as a half. Well, so that's cos of a half pi, sorry, cos of pi over 2. Well, cos of pi over 2 is 0. And this is sine of pi over 2, and sine of pi over 2 is 1. Bingo! Aye. That is what Demarvra's theorem is used for. Imagine if I had replaced that 3 there with a 10. Okay, then this suddenly would have become horrific, a massive binomial expansion. But if I'd done it in Demarvra's way, all that would have changed is that would have become a 10 there, and I would just have had to replace these 3's with 10's here, and the answer would have popped out in no time. How's about that? So Demarvra's theorem, really useful for finding powers of complex numbers. And like I say, we're going to discover that it does work for cases where sorry, I've just paused there for a moment. I don't know why. I was just reading through the example, make sure you're all okay. It also works for cases where n is negative and where n is not an integer, but we'll come back to that later. Okay, so I'm going to stop there and give you some work to do. Basically, what I'm going to do, I'll tell you now. Right, so this is another textbook from AQA. Okay, this is the FP2 textbook, and sorry about the shiny light. The FP2 textbook has got topics in it on complex numbers. Some of the topics from last course are in it as well, like finite series and stuff like that. But Demarvra's theorem, there's a whole section on Demarvra's theorem. We're going to be looking through that section. So what I want you to do, so I've just done the proof, which actually comes from a different section. But talk amongst yourself while I try and find the right spot in here. It's around about page 54. Have I gone too far? Oh look, roots. We've done them, haven't we? Nope, I'm not there yet. Here we are. So, Demarvra's theorem here. Okay, so they go on here to show why it's true in the cases where n is not an integer and where it's negative, which I haven't gone over with you, but that will eventually lead to this result here, which is the one I quoted at the start about it being true for positive and negative integers with fractional values of n. In other words, n belonging to the rational numbers. Okay, so that's the example I just went through with you. Okay, and then there are some more examples which I would like you to read through for yourselves. So there's one here about, I said about raising to the power of 10, so there's one here about raising to the power of 10. There's one here where you've got to be a bit careful at the start because it's not actually in the correct Demarvra's form because it's got a minus sign there. But that's easily dealt with, and if you read the solution you'll see, well, I think we've done something like that before. Here's one where the power is negative, but it still works. Okay, and then there's an exercise that I'd like you to try. On page 50 now. That's as far as I want you to go today. Okay. Hopefully that all makes sense. I'll put the instructions in the video for you so you can see exactly what to do, what to read, etc., 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 and have a go at starting this. If you've got any questions about the assignment as well, the polar coordinate assignment due next Monday, please feel free to drop me a line. Hopefully you've had a look at that and it looks okay. But if not, just let me know and I'll give you some help on that as well. I hope you found that interesting. Some really exciting things with Fermat's theorem coming up. The next section you'll see we'll be able to do things like that, which is interesting because it's got nothing to do with complex numbers, and yet we use something that's to do with complex numbers to actually solve that. We can find expressions for cos of n theta in terms of cos of theta raised to different powers of cos. Wow, exciting stuff. All to come. Have a good day.